Okay, great. So our first speaker is Antonin Raffin. So I'd like to introduce him. So he is a research engineer in robotics and machine learning at the German Aerospace Center, DLR. Previously, he worked on state representation learning in the ENSTA robotics lab, where he created the stable baselines library together with Ashley Hill. His research focuses on applying reinforcement learning directly to real robots, for which he continues to maintain the stable baselines 3 library. Antonin is joining us remotely today. Antonin, can you hear me?
Yes, can you hear me?
Okay, great. Do you want to share your screen? The floor is yours.
Thanks, it's already sharing. But maybe could you mute the mic? Because I got a big feedback in my ear.
Sure. So I'm going to mute him now. Let me know if you still have an issue.
You should be able.
Can you hear me? Is it any better? Antonin? Ah. Yeah, if I mute the PC mic, it seems to mute everything. Let me see if I can. Should I mute this? Shouldn't touch it. Okay, I think because we'll be quiet, hopefully it's okay.
Yeah, I can, okay, I can see that you see its slides.
Great.
Okay, so thank you for the invitation. Today I would like to talk about designing and running real-world reinforcement learning experiment, and that's actually my main focus here at DLR, at the German Aerospace Center, is bringing reinforcement learning to real robots, so training directly on real robot and avoiding simulation to reality transfer. And one thing I would like to keep you, that you keep in mind during the whole talk, but also that will serve you in other fields, is that boring problems are important. What do I mean by that? What I mean is usually when I see people trying to solve a problem with RL or with other technique, they have a particular problem in mind, which is very interesting for them, but also very complex. And as a result, they try to tackle it directly, and of course, it doesn't work. So one very important thing to keep in mind for everything you do, and especially when designing and running RL experiment, is to start simple and try to keep a thing as simple as possible. It might be boring at first, but it's very important for you to understand your problem fully and what works and what not, even on a toy problem. So yes, start simple and slowly build on complexity until you arrive to actually what you care about. And this so this thing of starting simple and keeping things simple, you can apply it to every aspect that I will present today. So why should we care about learning directly on the real robots, or why should you care about learning directly in the real world? One thing you might be aware of is we have perfect simulators, so we don't need to try things on robot. As an example, I was trying to learn to jump with an elastic robot in simulation as far as possible. I launched an experiment during the night, and when I came back, this is what I got. So it learned to perfectly solve the simulation, but it also hacked the simulator. And here, there's nothing wrong with the simulator. You will get the same other issue with other simulator. So one thing that is important is if you learn directly on real robots, you avoid the simulation to reality gap, and if it works, you can just directly deploy. So today I would like to guide you through the different steps in designing and running experiment. It will be about how to choose, how to design a task, how to design a custom task for reinforcement learning, how to choose an algorithm, and also some recent advances in reinforcement learning. How do you ensure? So about task design, actually 2 years ago, 3 years ago, I gave a much longer talk about reinforcement learning in practice with tips and tricks, and you can check it out online. Everything is available actually on my website, including the slides of this talk. So what you should care about when you design a task. So in reinforcement learning, you will have several things that you need to choose. And the first thing is the observation space. It is what you give to your agent. And of course, you need to give enough information to your agent to solve the task. And you should avoid at all costs to not break assumption, especially the Markov assumption. Because RL is not magic, and if you don't give enough information or if you break fundamental assumption, then it won't work afterward. Of course, like everything in machine learning, you need to be careful and normalize your observation space accordingly. The same thing goes with action space. So the action space will define what your agent can do, how can it act in the world, and here there are many compromises, and one of them is should you choose a small action space or a big action space? If you choose the action space too small, well, it will learn very fast, but then it will plateau or it will reach suboptimal performance. On the other hand, if you give an action space which is too big, then the search space will be way too much for the agent, and it will take ages to learn anything meaningful. And by choosing the action space the right way, you can also include some prior knowledge, include some bias to make the training faster. Again, and it's because many algorithms rely on probability distribution, you should normalize your action space. When it comes to reward function, start simple. Usually in reinforcement learning, that means start with a single term and try to have a shape reward, and only later on, if you need to tweak it more, you can add more complexity. And the last thing that I would like to talk about more in detail is about termination conditions. So when do you decide to end a trial? When do you decide to end an episode? And I would like especially to stop to pause on the difference between truncation and termination for infinite horizon task, which is usually the case in robotics. You don't want your robot to just reach a goal very quickly. You want, for instance, for locomotion, you want to control your robot all the time, and you don't have a fixed, a finite horizon. So to illustrate this difference between truncation and termination, which is actually very critical when you talk about performance, let's start with a sample example where you have a quadruped robot, elastic quadruped robot, and you want to learn to walk. Here it's on the treadmill, and the treadmill also define the tracking limits. You can ignore the rock, it's mostly for the photo. And here, so the reward is the forward speed of the robot. So you want your robot to walk as fast as possible in a straight line. And you have different cases where you will stop the trial. So one case is if your robot fall over, then you terminate the episode because you don't want your robot to break itself, and it also it's better to stop right now than to have something worse. Another thing is per episode you want to limit the maximum time per trial so that your robot explore more of the space, and this is what's called usually a timeout, and that's what you see in red here, like 15 seconds of timeout. And another way of stopping the episode is when the robot reaches the timeout. But in that case, it's an artificial termination. You should not penalize the robot for reaching the timeout. The same thing goes if the robot got off the tracking limit. It's not really the robot's fault. It's more a limitation of your experiment. And in that case, you should not penalize the robot. It's actually a good thing if the robot managed to reach the limits. How does that translate in practice, and why you should care about this distinction between truncation and termination? Let's continue with a very simple example where you have an environment where at every time step you get a reward of 1, whatever you do, whatever action. And let's say for the example you have a discount factor of 0.98, so gamma here. And in this environment we will set the timeout, so a max number of steps per episode, to 4. If you don't handle truncation properly, then if you compute the value function starting in the initial state, you will end up with a value of the initial state, whatever the policy, because here the reward doesn't depend on the action, of around 4. On the other hand, if you handle it properly and treat it as an infinite horizon task, by using the limit of geometric theory, then you can show that this value will be around 50. And here it's a huge difference on the very simple task. And you can imagine for other tasks that are more complex, this is also valid. Maybe as a quick showcase of how does it look like in practice for DQN. So the DQN loss is basically a regression loss where you want your Q value to be equal to some target. And as input, you have the state and action, and as target, then you have 3 cases. The first case is if the next step is not terminal, then you want to bootstrap. You want to use your value function to look of how does it look like after this time step. If it's terminal, then the target is just a terminal reward. And in the same case, if the next state is a truncated state, you still need to bootstrap because you don't want to penalize your robot, and you should pretend as if you will have an infinite horizon task. So that was about task design. Let's go towards choosing an algorithm. So when you choose an algorithm, you should usually think of 2 things. One thing is what type of action space do you have, because all algorithm cannot be applied to every type of action space. So are you using discrete actions? So do you have a finite set of actions? Or are you using continuous action, which is the case for robotics, where you have continuous value between 2 limits? And then the second thing you need to think about is, do you care about running the experiment very fast, in the sense that can you parallelize your training? Can you have, for instance, 1,000 of robots or 1,000 of instances in parallel, and you don't really care about sample efficiency? Or, for instance, for real robot, you usually have only 1 robot in the real world, and you cannot go faster than real time. And in that case, you would really care about sample efficiency. As a result, the go-to algorithm in simulation is usually PPO, because it's very fast, sample inefficient, but it doesn't matter when you have many simulation in parallel. And on real robot, now you have soft actor critic and its derivatives, so TQ, CTD3, and the more recent DrawQ or CrossQ, which are much more sample efficient and tailored for continuous actions. The main thing compared to PPU is that they require a bigger GPU, and it takes a bit more time. At the very opposite, if you have an environment which is very you can put really in parallel and it doesn't cost much, you can even go towards evolution strategy, so population-based algorithm. So that was about choosing an algorithm, and I want also to talk about recent advances in RL, especially with respect to runtime and sample efficiency. So you might have heard of it, but so recently there have been some improvements in just-in-time compilation for Python, especially using the JAX library, so which is developed by Google. JAX is an automatic differentiation library like PyTorch. And because of this just-in-time compilation and its design, which requires you to write things as a functional method, you can actually have some nice gain. So here I'm showing the same algorithm. One is using stable baseline 3 written in PyTorch, and the other one is using stable baseline JAX, so SBX for short. It's the same algorithm on the same environment. In x-axis, you have the time, so the runtime duration of training, and the y-axis, you have the performance, so the episodic return. And it's the same experiment. The main difference is because you compile the gradient update, you can go much faster. Here it's 10 times faster. And by having this huge boost, you can iterate much more quickly. In my case here, instead of waiting 2 hours, I'm just waiting 10 minutes to have a result. And that makes a big difference. The other big difference is because you can now do so many more gradient steps so fast, you can also do more gradient step and reuse and be more sample efficient. And that's the main idea behind DrawQ, which is a special configuration of soft actor critic, where you add dropout and layer normalization. So dropout to have an implicit ensemble and layer normalization to avoid gradient issues. In that case, on many environments, you can be much more sample efficient. So it will be slower because it does many more gradient update per step in the environment, but it can also reach the final performance much faster in terms of samples. And here, that's what you have. In x-axis, you have the number of time steps in the environment, and in y-axis, you have the episodic return. You should also have a look at some other advances, I would say, on top of TD3 or SEC, so TQC, which is an extension to distributional RL, and CrossQ, which is a very recent algorithm which removes the target network and uses batch normalization. And those are actually improvement over SEC. I would like to finish with an example of what you can do now with this very sample efficient algorithm. And some years ago, I was learning to work directly on the real robot from scratch on this elastic quadruped. And it took 5 to 8 hours. Recently, I used more recent algorithm, so using DrawQ and a bit more knowledge also about the task. And already in 5 minutes, it can learn to do its first step. And after it learns to do its first step, then in 10 minutes, you will reach, it will manage to walk forward, and it will then plateaus. And this is a good showcase of what you can do directly on a real robot using more sample efficient algorithm. One interesting part here is that between each command that I'm sending to the robot, I was doing 10 gradient steps. So here at a frequency of 30 Hertz, it's doing 10 gradient steps, and it's learning on the fly. And directly on the robot, so without any simulation. So how do you not break your robots? Let's start with a small example. So here I was again with the elastic quadruped. So it's a quadruped with some spring where you can store and release energy. And I was trying actually a dangerous task by design, which was learning to turn as fast as possible. And this robot is actually missing a hip joint, so it cannot really turn as other robot. It needs to find an innovative strategy. And because I was not setting the rotation, the angular velocity to the desired one, but I was really asking for dangerous behavior, it was meant to be dangerous for the robot. And this is what you get. So it learns to turn, but it's actually, it can fall very quickly. So how do you ensure that you don't break your robot? Because compared to simulation, things break and then you have to repair, and it takes quite some time. One way to solve that problem is by design. So if you choose the right action space, you can make sure that whatever action your agent take, you won't break the robot. As an example here, I was learning to control an elastic neck. So it's a neck made of silicone, which is controlled by 4 tendons. And you try to control the neck to achieve different 6D position. In that case, I could have controlled the motor position of the tendon, but there are 2 cases where that was dangerous. One case is if it's tensioned the tendon too much, then it can snap. Or if you don't tension them enough, then the tendon, the pose estimation will not be accurate enough, and it will be very hard to control anything. So for instance, here the design was to control tendon forces between two limits that ensure that the tendon are always tensioned, and that also ensure that they won't snap. And this is how it looked like on the rear robot. So this is the exploration phase. And after 2 hours of training, then it will reach the position very, very quickly. So that was some years ago. In the TV behind, you have in green the desired position, and you have in gray the position that it reaches. Again, this was done directly on the real robot because this kind of robot is actually hard to model. Another way to achieve safety is to have hard constraint and safety layers. This is actually what my colleague are developing on this robot called EDANT for assistive robotic. So you have a wheelchair with an arm on top, and you want to help the user solve different tasks. You don't want full autonomy because the user wants to be in control, but you also don't want to be fully in manual control because it's very difficult to solve some tasks. So instead, my colleague developed something called shared control template, which defines some mapping and constraints. So for instance, if you want to pour some water into a mug, when you're close to the mug, you will only allow rotation next to the tip of the mug, and you will not allow any translation. And by that way, if you have hard constraint, it's much safer than having soft constraint. So an example of soft constraint would be to give a negative reward for a bad behavior. The problem of soft constraint is that they can be violated by design. And if you have this kind of constraint, you can combine it with RL, but you can also combine it in something called shared control, where the user define where the arm should go, and the constraint and mapping does the rest. This was used in the challenge called Cybathlon, where here the user has to pick different objects, and those objects can be actually quite difficult to pick because they have different shape and they can be very small. Thanks to those hard constraints, this makes it much simpler and much more reliable in terms of performance. And you can see that thanks to those constraints, you can pick the different object reliably. All right, I'm presenting how to design a task, so choosing observation space, reward, and the rest. I've presented how to choose an algorithm and also the recent advances in RL. I've just presented the safety layer, and now I would like to talk about running the experiment in practice. So one very important thing when you run RL experiment is to have to use reliable implementation. By reliable implementation, I mean implementation that can be trusted and that can reproduce the original result of the paper. And this is the library I've been developing for the last actually 6 years. It's a stable Bayesian 3 library, and it provides a very easy to use interface for the user so that you can define, train, and save an RL agent in only a few lines of code. And we spend quite some time into making sure that we minimize implementation error. One main thing that we do is we try to follow software engineering best practices. So having type annotation, checking the type statically, having having a good code coverage, so covering our code with many tests. And also we benchmark all our algorithm, and we made sure that we could reproduce the original result. So this is for the algorithm, and usually when I do RL experiment on real robots, I combine it with something called the RL for experimentation. Basically, stable-based entry provide you with the main component for RL, so for instance, replay buffer or basic algorithm like SSE or PPO. And then the RL is in charge of training, evaluating the agent, saving everything that you need to reproduce the experiment, and it's also in charge of plotting and other metrics and making comparison easier. So the RSO is also very focused on having every experiment to be reproducible, so that you really save everything that you did to compare the different experiment and to, in case you need it, continue or reproduce one experiment. So it has training, loading, plotting script, and also hyperparameter optimization including. We have integration with different provider, including weight and biases for comparing experiment and sharing experiment. For instance, we have the we have a lot of runs on the OpenRL benchmark. And in case you want to apply RL to a new field, we have actually more than 200 pre-trained models with tuned hyperparameters. So if you can take a look at tuned hyperparameters and look if you look at your task and you try to find a task that is similar and start from those hyperparameters. All right, you've done the experiment, you've tried to follow everything I said, but it still doesn't work. What should you do? One thing, of course, is, as I said in the beginning, make sure you started simple, and in case you didn't try to simplify, because it's very important for you to iterate quickly. So if you have to wait 2 hours to know the results of a small change in your environment, this is not worth it. You should be iterating quickly, usually mean between having a run between 5 and 10 minutes or 20 minutes at most. So you should be able to quickly debug and know what's wrong. Another aspect you should very focus on is, did you follow all the best practices? So did you normalize the observation? Did you give enough information? Did you treat termination and truncation separately? Also, did you use trusted implementation? Or did you rewrite your own implementation? In that case, you might spend some time debugging it or with respect to references. And one aspect that also usually works, which is very simple, is just increasing the budget. So for instance, if you're training your agent for 1,000 steps, maybe try running it for 100,000 steps or more, and check that it's just not a problem of sample and that there's a real problem with the environment. And once you follow all the steps and it still doesn't work, then you might also consider some automatic hyperparameter tuning, for instance, using Optuna. The last thing that I would like to talk about, and it's also related to debugging, but not only debugging, is also having a minimal implementation. So what do I mean by minimal implementation? The idea of minimal implementation is you have a code base which starts to be complex, so you have 10, 15 files and 100 files, and you would like either to share it with others, or you would like to double check that what you're doing is what you think you're doing, or you would like also to have it to give it to someone to reproduce your experiment. And by minimal, I'm usually referring to something that is standalone with a minimal number of dependencies. By standalone, the best is usually to have a single file that showcase one feature of your bigger code base. So it will, of course, not reproduce the whole code base, but it will showcase a big feature. And for that, you need to reduce complexity. And by reducing complexity, you make choices. So for instance, if I want to share a minimal implementation of the PPO algorithm, I will only have an implementation that will cover, for instance, discrete actions and not also continuous action. And that will simplify the code, and that will make things simpler to debug and also simpler to share. Because when you have something that is minimal, you only need to look at one file. You don't need to look at 10, 100 files to understand everything that is happening. Everything is in this single file. It's also perfect for educational purposes when you want to study an algorithm or when you want to understand what someone is doing. And because you're reducing complexity and because you have everything at one place, it's make it much easier for you to find potential bug. And that's actually what happened to me recently. Is I was doing a minimal implementation of a method I developed, and I wanted to make sure that what I wrote in theory with what was done in practice. And I found a small inconsistency when doing the minimal implementation, and I could solve it both in the minimal code base and then also port the fix into the bigger code base. Of course, one thing to keep in mind is minimal implementation is not the solution for midterm, long term, because usually kind of duplicate things if you have multiple minimal implementation. So that makes it hard to maintain because you duplicate code. As an example of that, I was actually recently looking at what is the simplest baseline for locomotion, for benchmarking reinforcement learning on locomotion. And I was actually looking at an open loop baseline, something that doesn't depend on the state of the robot. And the idea was to study what is a good prior knowledge for robots and what is the minimal controller that can solve a task, and also get some insight about the shortcoming or limitation of reinforcement learning. In practice, it's very simple. It was using just one oscillator per joint of the robot, and those oscillators have a phase-dependent frequency. The frequency is shared between every joint. So it's a very simple method, but for implementing it on different cases, I had a code base which was medium, so 10, 15 file, and I managed to actually condense it to 30 file line of code. And by having only 30 line of code, I found out a small inconsistency, and I could then fix it back into the medium code base. The idea of this research, of this paper, was also to think about what is the cause of generality. So usually RL algorithm is very general, but that also means you spend a lot of time in designing the task, in making the task specific for this general algorithm. And here, with this simple oscillator, you have actually a very simple controller with a little bit of prior knowledge. So what I did is I compared sim to real transfer for the reinforcement learning algorithm without any randomization and without any reward engineering. And the RL algorithm, as you can see, will be able to solve the task perfectly in simulation by having a very high frequency control. And because the real robot acts as a low-pass filter, it doesn't really transfer well to it. On the other hand, if you have just a small prior knowledge that locomotion controllers are probably periodic, you can learn something open loop in simulation and transfer it without randomization and without reward engineering to the real robot. And it's very little prior knowledge. It's just saying locomotion controller should be continuous. So let's conclude. What did I present today? I presented some ingredients to design a task in reinforcement learning, what you should care about, how to not break your robot by giving you some example of safety layers you can implement. I also just shown you that you should leverage prior knowledge when you can, because this will maybe make the task a bit more specific, but you will avoid spending time in task design. You should make sure to have a reproducible experiment by saving everything that is needed to reproduce your experiment and to compare experiment. And that includes usually using the RSU. And I started with that and I will finish with that. Don't forget to start simple or come back to simplicity using minimal implementation. So thank you for your attention. Now it's the time if you have questions.
Antonin, can you hear me?
Yes.
Thank you so much for the wonderful talk. So if anybody has questions, raise your hand and we will reach out with a mic.
Hi, thank you for the nice talk. I have a question about the real robot training. In the case of real robot training, when the training happens, for example, do you train the robot every step, or do you collect the trajectory for a while and then train, or at the end of every truncated episode, or can you tell me how you did it?
Yes, so actually what happened is in the past I used to train after every episode. But then with more recent algorithms, so using JAX, I was training at every step. So every time you stay in the command, I was training. And depending on how fast is your computer or not, what I do is either wait for an episode to be over and then I can have a thread that is training asynchronously, or if the computer is fast enough, then I can really train on the fly and do not break the control frequency of the controller.
I see. So training is happening on an additional computer or on board of the robot?
So for now on the computer, but
Okay.
then it can be deployed on the robot.
Okay, thank you so much.
Thanks.
Thank you. Any other questions?
To what extent do some of the issues that you've shown between simulation and real world, to what extent do you think they can be fixed by building more accurate simulators?
Well, it depends on your task. So for instance, you have, now you probably have seen that from ETH Zurich, if you spend enough time on the simulation, if you spend enough time on identifying your system, learning an actuator model to really reproduce what's in the real world, and to spend enough time randomizing in a smart way your simulation, you can probably solve a lot of problem. But for any new robot, you will have to do that again and again. And also some tasks or some robots are very hard to model. For instance, that was the case for the elastic robot. The elastic component is not that trivial, and then the friction in the motor is not the same for every motor. Or also, for instance, for peg insertion task, it's those type of contact forces. Modeling contact is still pretty hard, and maybe you need too much randomization. So you can probably solve a lot of problem, but for any new problem, you will have still the cost of redesigning, identifying, and still having this loop of hoping that you randomize enough, you have identified your robot well enough, and try it out in the real world, or it doesn't work, then you need to again. That's the main, I would say, interest in learning directly in the real robot. On the real robot is you can remove that part, you can remove all the modeling parts and just focus on solving your task. Of course, you have other problem, as I shown, that you can break robots, you cannot parallelize, and you need to be very careful with the robot.
Thank you.
I think we got a couple more questions.
Yeah, I have maybe the opposite question about the on-board or on-platform training. Suppose you were trying to do on-platform training, but you were in a situation where the robot's every move was being scrutinized for safety, maybe because it needs to operate in a crowd or something. For that onboard training, you mentioned a few different like techniques for incorporating like safety barriers, and I just wanted your opinion on which one you think is like most promising and why.
I'm not sure to fully understand the question of what technique are you talking about for
Yeah, like
I think
let's talk about like the on-board training problem, but now I put a physical obstacle like old lady crossing the street, to use something a little bit contrived. So how would you try to impose safety for your walking robot with that kind of environment?
Yeah, okay, thanks. Maybe, so in that case, it sounds more like deployment, and I would probably have some kind of at least supervision or soft supervision by some human on the side, because I think it would be also the same as for autonomous driving. It's very hard to cover all the possible cases in the safety, and usually having some human supervisor, even though the supervisor doesn't have to intervene all the time, would be a potential solution, although it would still require some constant supervision. At least for the example that you're proposing, that's what I would have in mind. Or what you can probably think of is the same way I've shown for the assistive robot, is not have a fully autonomous robot, but a shared control robot. So the human can take over, or you can guide the robot where you want. So most of it is done autonomously, but the tricky part can be assisted by the human. And yeah, that's what I have in mind, at least for your question.
So I have a quick question. So you talked about sample efficiency from different directions. So you mentioned implementation-wise and time it takes to converge or get a good policy. And then you also showed this cute robot that found a legged policy within a few minutes compared to maybe vanilla Q learning, which might take a long time. So if you, like, do you feel like, I guess it's a broad question, so the sample efficiency problem, how do you think is the best way to approach it, or how far are we from solving something that, you know, maybe is in a model-free manner, learns a policy rapidly? So is it still a problem? Is sample efficiency still a problem in your mind, or do we have all of the ingredients today to address this kind of long exploration and interaction stages before you learn a proper policy?
Well, I would say it depends on the task. So I would say for now, for simple tasks like walking and nothing fancy like jumping or dangerous, I would say we do have the algorithm, or at least it's possible now to learn in the real world, but you still need to spend some time making sure that you won't break anything. And another very important thing I only covered very briefly is to not forget to add prior knowledge when you can, because it's very nice to learn from scratch and to hope that you will find a totally novel behavior. But usually when you learn from scratch, that's when you you lose a lot of sample relearning something that you already know. And that was the case for locomotion. If you already know that for locomotion you just need a periodic policy, you should probably not spend too much time relearning that and only learning what you don't know. And yeah, with a recent algorithm, I have the feeling that now you can tackle a lot of problem much more quickly in a reasonable number of episodes or samples. Yeah, but it also boils down a lot to how do you design your task and how difficult do you make it for the robot to learn.
Great, thank you so much. Any other questions? for Antonin. Have you tried to run the policies on kind of high fidelity? So maybe something with stable baselines 3. Have you tried to run it on high fidelity simulations? Higher fidelity than the ones you've shown here. You know, I guess some of the most recent ones. Same task. If you still notice it to hack the simulation, or is it a more an artifact of like older environments that are not that well designed?
Yes, well, it all depends how you define, how you define your environment. And here it's not the simulator. The simulator is fine. It was mostly fun. Here, what I shown is that I didn't model the motor dynamics, so the motor was allowed to go as fast as possible. And also, this type of behavior, you can also see it in the real world if you're not careful. This problem of trying to have this high frequency noise, actually I work on that, is something used by default now in the RL community because you don't see it on the real robot, but it's terrible if you try it. So some of those problems are actually in the algorithm and not in the simulator. So this high frequency noise, yes, high frequency exploration is the default one, and it's terrible for any real actuators. And hacking the simulator, actually there's a paper about that with many researchers from the last 20 years. It doesn't really depend on the simulator. There's always a way to hack the simulator because simulators are not perfect. But by being more careful, or by, in my case, it would have been using a more accurate model of the actuator, or using a low-pass filter, then you will also reduce the number of problems, and you will make it harder to hack the simulator, or hack also your reward. But now if you look actually at recent papers in RL, there's a lot of time which is spent into reward engineering, so maybe the simulator is more close to the real robot, but you still need to spend a lot of time so that it doesn't optimize for a reward that doesn't solve your task. So I don't really think it's a simulator problem.
Great, thank you so much. I have a lot other questions, but we'll let you go and change over for the next talk. So thanks again, Antonin.
Thanks.